recording for today, and we're going to get into, let me make sure it's recording. It is. Okay, we're going to get into the topic for today, which is random variables. I will tell you that depending upon the instructor you had, or when you had elementary statistics, you may or may not have seen some of this content. Okay, this is probably one of the first lessons where there's some content that is not typically covered in Math 1401. So I want to start with an overview of what we're going to be talking about throughout this particular lesson, and it'll take today and Thursday to cover it. It'll take 2 lessons, but we're going to be talking about what are called probability distributions. And sometimes students think that probability is out of place when you think about statistics, but quite honestly, probability forms the foundation for everything that we do in statistics. So it is an important part. And so we're going to talk about specifically what are called probability distributions. Earlier, not necessarily in this course, but in Stat 1401, we often talk about how to take data and organize it into a table form. And that table form in statistics is called a frequency distribution. And we have talked about how we can organize data into tables. But those tables or frequency distributions become kind of a jump start to the graphs and things that we create. And a frequency distribution actually shows us what happened. For example, if we were looking at flipping a coin, a frequency distribution would tell us how many times we flipped a head and how many times we flipped a tail. Okay, so it shows us, a frequency distribution shows us the reality of what really happened. In this lesson and throughout the next couple of lessons, we're going to be talking about a probability distribution. A probability distribution describes what should happen based on an assigned probability for every possible outcome of a particular event. Again, let me go over and kind of, again, give you an example so you can maybe see it. Again, for example, let's say that our experiment is that we're going to flip a coin. Well, if we consider our frequency distribution, let's say we're going to flip a coin 10 times. Okay, our frequency distribution would actually show us heads and tails, and it would show us how many times, how many heads we got. Let's say we got, I'm going to make it up, 7 heads and 3 tails. Okay, so that represents our frequency distribution. On the other hand, though, a probability distribution shows us the probability, or what's the chance that we would get ahead. Well, hopefully you understand that there's one way to get ahead out of the 2 things and one way to get a tail out of the 2 things. Again, the expectation would be if I flip a coin 10 times and I expect to get ahead half of those times, I would expect, based on the probability, to get 5 heads and 5 tails. Now, obviously, that doesn't often happen in reality. Okay, so the probability distribution gives us an idea of what should or could happen for a particular event. You can see a probability distribution in a table form similar to what I just drew. It can also be in a graph form, and there are formulas for calculating probability distributions. And so we're going to focus on probability distributions. This particular diagram, it actually came from a different textbook from years ago, but again, it gives you, again, that idea of, okay, earlier lessons, we talked about how that we could collect the sample, roll the die so many times and record how many times we get a 1, a 2, a 3, a 4, a 5, or a 6. We know that the probability of rolling a 1, there's one way out of 6 things and so forth, and we can calculate the probability for each event so that we ultimately get this theoretical model of what should happen when we roll a die. And guys, so this stuff is used like by insurance companies to determine the rates of your insurance, because they look at things like your age, your gender, have you had accidents previously. So they kind of use this idea of probability, what's the chance you're going to have an accident if you're in the 20 age range, or if you're in the 30 age range, or if you're a female, or if you're a male. And so they take all that into consideration, and we get this theoretical model. So the probability distribution gives us, in theory, what should happen if everything works kind of the way it's supposed to, so to speak. So again, as I was just mentioning, a lot of the decisions that are made in business, insurance, other real life situations are made by assigning probabilities to all the possible outcomes that could happen for that particular event. One example can be a saleswoman or a salesperson can compute the probability or the chance that she's going to make 0, 1, 2, or 3 or more sales on a single day, or she could look at it in a single month. And then she'll be able to compute her average number of sales per week, and if she works on commission, and then she can figure out kind of how much her weekly income is going to be. Again, that sounds like a lot of work, and it would be, especially if you were not necessarily math oriented. But again, that can help the salesperson or the saleswoman kind of predict what her check, her pay is going to be over a period of time, so that she can probably plan a budget and budget appropriately. And we'll look at several other different examples as we go throughout the lessons. There are two different types of probability distributions. And typically in Stat 1401, we focus primarily on what are called continuous probability distributions. But we are going to include in Stat 2401, this course, a discussion of the discrete probability distributions. So I want to kind of give you an overview of those two different types, and then which ones we're going to focus our attention on. So a discrete probability distribution, much like discrete data, has a countable number of possible outcomes. Think about rolling the die. There are 6 things that could happen. Think about flipping the coin. There are 2 things that could happen. In today's world, think about taking a COVID test. You could get a true positive, a false positive, a true negative, or a false negative. So there's like 4 things that could happen. There are a countable number of possible outcomes. Those probabilities are either determined theoretically through a formula. I mean, obviously, if I've got a coin, I have 2 options. or if I have a die, I have 6 options, or they can be determined by observation over a period of time. We rely on a rule in statistics called the law of large numbers. If you do an experiment enough times, you can get an estimated value or an estimated probability based on that. It's called the law of large numbers. The more times you do something, the better your approximation. We can show or create a table or a graph for a discrete probability distribution. There are also some formulas, but we don't rely on those too much. The primary requirements for a discrete probability distribution really stem back to the basic rules of probability, which are the probability of any outcome has to be between 0 and 1 inclusive, and then the sum of the probabilities in the sample space equal 1. Okay, let me kind of show you what I mean by that. Again, there's a little bit of an assumption here that you do have a basic idea of probability. Okay, so the basic rules of probability say that all probabilities have to be between 0 and 1, and that does hold true for a discrete probability distribution. So if we go back here to our example of flipping a coin 10 times and look at this, okay, notice that for heads, we had 1/2, which we could have written as 0.5 or as 50%. Okay, so those two values are in between 0 and 1. If we add those two things together, when we flip a coin, the only two things that can happen are heads or tails. If we add those probabilities together, 1/2 plus 1/2 is a whole. Okay, so they have to total to 1, and they have to be between 0 and 1. Let me remind you, just in case you've forgotten from standard probability, that a probability of 0 means that the event is impossible, that there's no way, no how that a particular event is going to occur. For example, if I were to tell you, what's the probability we're going to roll a 7 on a die? Okay, a die is 2 dice, 1 die, 6-sided cube. You're never ever going to roll a 7. If I tell you what's the probability that Thanksgiving is on a Sunday, at least within the United States, Thanksgiving is never, ever on a Sunday. On the flip side of that, the probability of 1, which is the maximum you can have, means that the event is certain, that it's going to occur no matter what you do. And then we can have any value in between that. Okay, so we have value of 1 means it's certain. So for example, again, thinking about the die, that if we say that we roll a number less than 7 on a die. Well, again, it's a 6-sided cube numbered 1 to 6. All the numbers are less than 7. So no matter what, I'm always going to roll a 7. I could tell you the probability that Easter is on a Sunday. And there again, within the United States, Easter is always on a Sunday. So that's a certain event. No matter what happens, that event is going to occur. So again, we think about when you're thinking about probabilities, and even within probability distributions, again, think about this like a graduated scale. You have 0 to 1, and you can have any increment, any decimal, any fraction in between. Of course, the halfway point would be 0.5 or the 50-50. Okay, and then again, you can have any value in between. The closer you are to 0, the less likely, okay, if you're close to 0, the less likely an event is going to occur. The closer you are to 1, the more likely that event is going to occur. Okay, so that's kind of a quick basic review of some probability, but those characteristics from general probability carry over to our discrete probability distributions. They have to have probabilities between 0 and 1. It will never be bigger than 1, and it will never be negative. And the total has to be 1. Again, it's not going to be, we talk sometimes about giving 110%. Well, statistically, guys, you cannot give more than 100%. Hence, it cannot total to more than 1. The second type of probability distribution we talk about is a continuous probability distribution. The difference is a continuous probability has an infinite number of outcomes between two given values. Again, it's things that can be broken down into fractions. Things like, think about time, because I could break it down from, years to months, weeks, days, hours, minutes, seconds. So I can break it down. It's on like a continuum scale. Typically with continuous probability, the probabilities are determined theoretically. I have had a course where those probabilities for continuous probability are determined using calculus. Okay, we don't have to do calculus in this class, but it can be done theoretically using a formula, but it requires calculus. We also can show or visualize a continuous probability on a table or a graph. And you have really the same two requirements, but they're worded differently. You still have the idea that the probability of each outcome is between 0 and 1. So if you're looking at it visually, that means that you're kind of that vertical bar on your bar graph, okay, is going to have some height. It's going to be between 0 and 1. So again, you can still have any value, fraction or decimal. When we think about the idea that the sum of the probabilities is equal to 1, when you think about it in terms of the continuous probability distribution, we think about it in terms of area, and that the total area under, quote, the curve is 1. And I'm going to be able to show you that when we get to the discussion of continuous probability distribution. So if you'll just hold on, I'll be able to show you that. But it's the same two requirements, that all the probabilities are between 0 and 1, and all the probabilities total or add to 1. They're just stated in a different form for the continuous probability distribution. There are a variety of discrete probability distributions that are used throughout statistics, as well as continuous. We have just a general discrete probability distribution, which we are going to look at in this lesson. We also talk about binomial, which we're going to talk about in this lesson. Two others are Poisson and one called hypergeometric. We don't talk about those in this course. Again, if you go into an area of study, if your major requires you to have a strong background in statistics, you can actually take an entire course on probability distributions, an entire course on discrete, and an entire course on continuous. So again, we're just still kind of touching the surface, but introducing you to some of the more commonly ones that are used. For continuous, we actually look at a few more. We do the uniform distribution, which we're going to look at here in Module 1, the exponential distribution, the normal distribution, the student's t-distribution, chi-square, and then the f distribution. And I think that's all of them. Yeah. Okay. And again, we look at more of those because there's more things you can do with a continuous, and you can actually sometimes the discrete can be modeled using primarily the normal distribution. Normal distribution is probably the one that is used most often throughout statistics. Okay, any questions? That gives you a broad overview before we get into specifics. Okay, our focus today, and I hope we can get through both of them, we're going to look at specifically the discrete probability distributions. I'm going to start with kind of the general ones, and then we're going to move into binomial. Any questions? Okay, our objectives are that hopefully by the end of the lesson, you're able to recognize and understand discrete probability distribution functions in general. If you're given it a scenario, you can represent it as a discrete probability distribution and calculate the mean and the standard deviation. Can also calculate and interpret expected values, and then also do the same thing for the binomial probability distribution. So again, we're going to focus initially on discrete probability distributions, and specifically kind of just the broad category of a general type discrete probability distribution. Again, just to reiterate, a discrete probability has a countable number of possible outcomes. We can display it as a table or a graph. The probabilities are determined theoretically or by observation. And the two main things for you to remember is that all of the probabilities must be between 0 and 1, meaning your probabilities will never be negative and they will never be greater than 1. And the sum of the probabilities in the sample space must equal 1. Okay, I'm going to give you the formulas here for the mean and the standard deviation. These are for the general probability distributions or general discrete probability distributions. You will be doing hand calculations using a calculator. Minitab does not do the general probability distributions. You will need to have a handheld calculator that will at least multiply and divide and take square roots. So the mean, and I've given you the formula here, mu is the Greek letter that represents the mean for any distribution. This big funky looking E symbol in mathematics, it's the Greek letter, and let me get here where I can make some write on it here for you. This big Greek letter here, this funky looking E symbol, is the Greek letter sigma. And mathematically, whenever you see that symbol, it means to add or total the values that it's talking about. So this is telling me to add together the mean times the probability of X. So I kind of wrote it out in words here for you. You have to multiply each X times its probability, and then you add up the results to get the mean. This Greek letter here, in case you didn't catch it, is the Greek letter mu, and it always represents the mean of the population. The standard deviation, it looks a little scary, but it's really not, okay? This symbol here, again, it's kind of weird. This is also sigma. Okay. The big funky looking E is kind of like the capital or the big sigma. The little O with the curl is the lowercase sigma or the little sigma. Okay, but it's the square root of x minus the mean squared times the probability of x. And so again, I kind of wrote it out. You subtract the mean from each x, square your answer, multiply that times its probability, and then you add all the results. And once you get them all added up, you take the square root. And again, we're going to do that, but I'm going ahead and giving you the formulas here. Okay, and again, this is something you're going to have to do kind of by hand using a calculator. All right, so let's kind of dive right in. The question says, does this scenario represent a discrete probability distribution? And so it reads, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. And then it tells us we're going to let X be the number of times a patient rings the nurse during a 12-hour shift. And our possible outcomes are they could ring it 0 times, 1 time, 2 times, 3 times, 4 times, or 5 times. And then based on the data that they collected, they've given us the probability for each of those values. Okay, so how do we decide whether this is a discrete probability distribution? What do we need to do? There's really two things. We have to confirm those two characteristics that I've mentioned several times. Okay, we have to be sure that all of our probabilities are between 0 and 1. So if I scan this list, they do all appear to be, they're all in decimal form, and they all appear to be between 0 and 1. I don't have any that are negative, and none of them are above 1. So I've met that requirement. Then I need to check the second requirement. The second requirement is that if I add all of those probabilities up, they have to add to 1. Now, you can do that on your calculator. For demonstration purposes, I'm going to try to do it right here in my head. 8 and 6 is 14, 15, 16. 8 more would be 24, 25, 26, 30. So 0, carry my 3, 3, 4, 7, 8, 9, 10, 0, carry the 1, 1 plus all those zeros is 1. So they do add to 1. So I've met that requirement. So this scenario does represent a probability distribution. My computer said something about I was having an internet issue, so it might be on my end. Is anybody else having trouble with audio?
Not really, but it has frozen a few times.
Okay, I'm sorry. Y'all let me know if it gets worse, okay? But this scenario does represent a discrete probability distribution. And then they could ask us questions about this thing, because I could ask you probability questions. Like, I could say, what's the probability that the average post-op patient rings the bell 3 times? Guys, don't overthink it, okay? Because basically they've given me the answer. I just have to read it off the table. It would be 0.28. Okay, let's go on to the next one. Okay, it says a company wants to evaluate its attrition rate. In other words, how long new hires stay with the company over the years. They have established the following probability distribution. And they tell us that X is the number of years a new hire will stay with the company. And the probability, or P of X, is the probability that a new hire will stay with the company X years. Okay, so they've given us a table, and so they've shown if a new hire will stay 0, 1, 2, 3, 4, 5, or 6 years. And then based on past histories, they've determined the probabilities. But it looks like one of the probabilities is missing. Okay, so I'm going over to my piece of paper. I copied this question earlier onto my paper so we could talk about it. Okay, so we have this distribution. It does appear, at least initially, for what I have, all of the values are between 0 and 1. And so the first question they ask me, because I need to know what the probability is when X equals 4. What's the probability that a new hire is going to stay 4 years? Guys, how do you think we can figure that out?
Would we subtract all of them to equal 1 still?
See, you're right. Remember, this column has to total to 1. So if I add up all the things that I know, okay, if I subtract what I know, okay, whatever's left has to be that 1. So if I take those numbers, and I'm going to go over to my calculator, okay, I'm going to add them up first. So I have 0.12 plus 0.18 plus 0.30 plus 0.15 plus 0.10 plus 0.05, and I hit enter. That gives me 0.9. Well, I know it has to total to 1, so 1 whole minus 0.9 gives me 0.1. So the probability that they stay 4 years is 0.10, and that equals the probability of 4. If you have a piece missing, you know the probabilities have to total to 1. So if you subtract what you know from 1, that's going to be that probability. All right. What if they ask you, what's the probability that a new hire is going to stay more, let's see, greater than or equal to 5? So they're going to stay 5 or more years. Okay, please make sure you interpret this appropriately. This is greater than or equal. So in this scenario, how long could they stay?
Is it 0.15?
It is 0.15 because they could stay 5 years, because it could be equal, or greater than, they could say 6. So you're right. We're going to add together the value for 5 and the value for 6, and you are correct. It is 0.15. So the probability that a new hire stays greater than or equal to 5 years is about 15%. All right, let's look at one more. What's the probability that they stay less than 4? Guys, again, you really have to pay attention to these symbols because this symbol represents just less than. So would I include 4 in the calculations? No, because it's not equal to. So I'd have to consider less than 4. They could stay no year, 1 year, 2 years, or 3 years. But because it's less than 4, it does not include the 4. Okay, kind of use your basic, not to be ugly, but common sense. Okay, make sure you interpret the symbol correctly. So if we add those together, we have 0.12 plus 0.18 plus 0.30 plus 0.15, which is, I believe when we get all that added together, is 75. 30 and 30 and 0.15. So this is about 0.75. So there's about a 75% chance that a new hire would stay less than 4 years. Guys, don't overthink it. The information there is pretty much given to you on the table. You're interpreting it based on the question that is asked, but please be sure that you interpret the mathematical symbol correctly, whether it equals or does not equal. Okay, with the same question, let's look at how you would calculate the average, because the question might be, on average, how long would you expect a new hire to stay with the company? Okay, that word average, remember, is another way to refer to the mean. So that question is actually asking us to calculate the mean. Okay, and I'm going to write it out longhand so you can see what we're doing in terms of that formula. Some people like to do it in a table form, so if you prefer, you can do it in a table form. Okay, I'm going to do X times the probability of X. Okay, so I'm going to take the number in the first column and multiply it times the number in the second column. So 0 times 0.12 is 0. 1 times 0.18 is 0.18. 2 times 0.30 is 0.60. 3 times 0.15 is 0.45. 4 times 0.10 is 0.40. 5 times 0.10 is 0.5. And 6 times 0.05 is 0.30. Okay, so I've taken each number, each X, and multiplied it times its probability. Now, again, I wrote it out longhand. I'm then going to take, the second step is to take the list of those answers and add them together. So I'm going to add these up. Okay, so I have 0 plus 0.18 plus 0.60 plus 0.45 plus 0.40 plus 0.50 plus 0.30. And I definitely want to get my calculator out for that. I'm going to use my handheld so I can see the numbers. So I have 0.18 plus 0.60 plus 0.45 plus 0.4 plus 0.5 plus 0.3, which gives me 2.43. So the mean time that someone would stay is roughly 2.43 years. Okay. Then it also asks us, what is the standard deviation? Again, this is kind of one of those manual calculations. And a lot of people, again, it helps to create this table because you've got to take the X minus the mean and then square it. Okay, our mean is 2.43. We just calculated that. So I've got to do 0 minus 2.43 and square it. So that's negative 2.43 squared. I'll come back and square it in a minute. 1 minus 2.43 squared. Okay, 1 minus 2.43 is negative 1.43. 2 minus 2.43 squared is negative 0.43 squared. 3 minus 2.43 squared. Okay, so 3 minus 2.43 using my calculator is 0.57 squared. 4 minus 2.43 is 1.57 squared. 5 minus 2.43. We probably could set us up an Excel spreadsheet, but that takes some time. But if you wanted to do that, you could have it do that. Okay, 2.57. And then 6 minus 2.43 squared is 3.57 squared. Okay, so then I've got to take and square those numbers and multiply them times the probability. See, it gets messy. Okay, so I really need all of these numbers squared times the probability. Oh my. Okay, so, and you can do it in your calculator. Again, you can get you out a spreadsheet. So I need another column out here, but my draw has stopped working all of a sudden. Are you guys there? I feel like I'm having internet issues.
No, it's been good.
Okay.
Yeah, see here.
Okay. All right. Let me see. I don't know why it's not letting me draw anymore. Okay, so I'm going to try to go out and do this on my calculator to save us a little bit of time. Okay, so we would have.
Actually, I have a quick question. Sorry to stop you there, but
okay, that's fine.
I was going back because I'm trying to do this along with you, and I'm not getting I didn't get the same answers for the x minus m squared. So I'm not sure what I'm doing wrong there. Can you show me, I guess, how you got those answers?
Okay, wait just a second. Let me go back to my paper. For what?
Yeah.
X minus
so
the mean.
for that part right there, yeah, when I'm squaring it, I did not get those same
okay,
answers.
I haven't given you the squared answers yet.
Oh, okay. I'm sorry.
I haven't squared them yet. But something's going on and my tablet's not working for some reason. So let me see if it'll work now. Oh my goodness. Okay, so I've got to square these numbers and I haven't squared them yet. So that's probably what's throwing you off. So let's see if I do negative 2.43 squared. Okay, did you get 5.9049?
Yes.
Okay, and so that gives us that number. And again, for some reason, my lovely tablet has quit letting, oh, there it is. It's back again. Now it's not back. Okay. All right. So when we square this, I get 5.9049. Okay. Let me draw me a line out here. This is taking way too long, but we'll get there. Okay. And then we do negative 1.43 squared. You should have gotten 2.0449. 0.43 squared, 0.1849, 0.57 squared is 0.3249, 1.57 squared is 2.4649, 2.57 squared is 6.6049, and 6 minus 2.43, the 3.57 squared is 12.7449. Okay, so did you get those numbers? Are we together now?
Yes.
Okay, good. All right. Then, whoo, I'm still not finished. I got to take each of those numbers. I got to take that value, x minus the mean squared, and multiply it times the probability. Okay, so I'm going to do 0.12, okay, and I'm using the probability. So I got to do 0.12 times 5.9049. I'm gonna create you guys a spreadsheet to do this. 0.708588, 2.0449 times 0.18. You get 0.368082. 0.3 times 0.1849 is 0.05547. 0.3249 times 0.15. Abigail, are you still getting the same numbers as me?
Yes.
Okay, so we're on the same page. 2.4649 times 0.10 is 0.24649. 6.6, okay, so 0.66049, and then 12.7449, 9 times 0.05. 0.637245. Okay, so now we got them all multiplied together, and I need to add those numbers up. Okay, that last column there, I'm going to add them up. So I'm going to add those numbers together. Okay, when I get them added up, I get 2.7251. Anybody disagree? And finally, woo, the last step is to take the square root of that answer. Okay, so the square root of 2.7251 is 1.65 0.078. We usually will round to 2 places, so our standard deviation is 1.65.
And you said Minitab can't do this, right?
I
So
don't
this is
think
all hours.
Minitab doesn't do this, but Excel will, and I'll try to create a spreadsheet where you can plug the numbers in so that it won't be so cumbersome. But at least doing it this one time by hand, hopefully you can see what we're doing. It just takes a long time. Honestly, this is the way that when I learned it, how I had to do it. I had to do it by hand with a calculator. But we do have Excel now, so I'll try to create a spreadsheet where you guys can plug the numbers in.
Okay, thank
But
you.
hopefully you can see the process of what I'm doing.
Yes.
Is there like a special way that you're supposed to enter like the last column right there of numbers, the x minus m squared times px? Because when I tried to add all those in my calculator, it gave me an error. Like adding all the decimals.
There shouldn't be a special way to enter it. Were you entering the actual 0.708588?
Yes.
Or were you trying to do the multiplication and stuff all at one time?
I just tried to like add that whole last column together.
I'm not sure, Abigail. There shouldn't be a special way because I just entered it into mine straight out. I would check to see if maybe you had, maybe if you typed something incorrectly, sometimes that'll give you an error. Like if you put an extra plus sign in there or an extra decimal point or something, sometimes it'll give you an error.
Yeah, I'll go back and try it again then.
Okay. But do you understand how to use the formula? Again, I'll try to create a spreadsheet that'll make it easier.
Hey, Laura, or Ms. Ralston, that last column, so the last column is it's taking that times the p of x. Okay, so it's
Yeah,
like
it's doing
okay.
the
so
last column. I'm
100.
doing this number times this number.
Okay. And then you add those all together and then take the square root.
Yes, ma'am.
Gotcha. Thank you.
Other questions? Okay, so that kind of gets us through the discussion of kind of the general. The biggest thing to remember about the general discrete probability distribution, all probabilities have to be between 0 and 1. The sum of the probabilities is 1. And then pay attention to your symbols, whether it includes, like it includes equal, which would include the number, or it does not include equal, which means it does not include the number if you're asked to calculate a probability. Okay. The other discrete probability distribution that we're going to talk about is a binomial. And I may not get through it all today, but the nice thing is Minitab does do binomial. Okay, because binomial is probably one of the more popular distributions that's used in statistics. And so I want to give you some examples of where we can use a discrete probability distribution, specifically a binomial. Again, there's lots of events or experiments where you have just 2 outcomes, or we can, in a sense, force or reduce it to 2 outcomes. I mean, this morning we've talked about tossing a coin, heads, tails. A baby is born. Biologically, the baby is born and they're either a boy or a girl. Any kind of sports game, you have win or a loss. You can have true false on a quiz or a test. With medical treatments, we can talk about whether the treatment is effective or ineffective. You have blood pressure that's normal or abnormal. Even rolling a die, we can force it to be a binomial because we can say we get 5 or not 5. We either get what we want or we don't. Even a multiple choice question where you maybe have 4 or 5 choices, again, can be reduced to a binomial because you can say, I got it correct or not. So a binomial is one that's used a lot because we can either have 2 outcomes only, or we can force it to have just 2 outcomes by how we define the 2 categories. So a binomial experiment has to satisfy 4 different requirements. One is there must be a fixed number of trials. You have to tell me, I'm going to flip the coin 10 times, or I'm going to roll the die 50 times. I'm going to look at 100 patients. You have to have a fixed number of trials. And each of those trials has exactly 2 outcomes. We typically refer to those as a success and a failure. A success means you get what you want. Now, that may not necessarily be a positive thing, because if my success is that the medical treatment is ineffective, well, being ineffective is not a good thing, but in the way that I set my experiment up, that is what I'm considering a success. Usually that success is represented by a lowercase p in terms of the binomial experiment. It's just a symbol for P is success. Failure means you don't get what you want, and it's represented by Q. And those 2 probabilities together, the probability of success plus the probability of failure, has to total to 1. Okay, that's why the formula Q is 1 minus P, because oftentimes they'll tell you the probability of success, but you're not told the probability of failure, but you can figure it out because the 2 together have to total to 1. The third requirement is that each trial must be independent, meaning that whether or not I get ahead on the first flip doesn't affect whether I get ahead on the second flip or the third flip or the fourth flip. Or if we're rolling the die, the fact that I get a 5 on the first roll doesn't affect whether I'm going to get a 5 on the second roll. That basically the outcomes do not affect each other from trial to trial. The probability of success must remain the same for each trial. So we're flipping the same coin every time. We're rolling the same die every time. Okay, you're not changing it. This would be especially important if you're doing something where you are maybe drawing, say, cards out of a deck, and you have to make sure you put the card back so that you always have 52 cards in the deck. If you're drawing without replacement, then that's a problem. It's not going to meet those 2 requirements because you're changing the makeup or the contents of the deck if you don't put the cards back. Okay, so for a binomial experiment, we typically do have to sample with replacement. Now, there are some ways to get around that, because if you've got, 1 million people and you take 1 person out, that really doesn't make a big difference. Okay, or even taking 2 people out doesn't make a big difference. So sometimes if you have a really large sample, removing 1 and not replacing it doesn't affect it enough, and you can still use the binomial experiment. Okay, so you want to make sure you have those 4 requirements: fixed number of trials, 2 outcomes per trial, they have to be independent, and the probability of success remains constant. Now, binomials can be done with a formula. We are not going there. We are going to let Minitab do the work for us. It uses this formula, okay, but we're not going to do that. But it is these are based on a formula and the number of successes you would get and the number of failures you would have. Okay, I give you the steps for putting it in Minitab and so that you can see it here on the screen, but we'll walk through it together. Probably not today because I'm probably going to run out of time, but we'll pick back up with that discussion on Thursday. This table needs to become your best friend. Okay, because this table tells you how to read the results that we're going to get from Minitab. And again, it's important to pay attention to whether the question says exactly, at most, fewer than, at least, more than. It tells you how to calculate your results. Miss Ralston does not even keep in her mind how to do these. Now, after a while, you'll get used to it after you do enough practice problems that you may not need this table, but you need, I would tell you to print this off. Let me tell you what slide number it is. This is slide number 15. If you don't print anything else, I would tell you to print slide 15 and have it next to you as you're working the problems on the quiz, as you're working the problems on the midterm or on the test, that sort of thing. There are formulas for calculating the mean and the standard deviation, and I do not think Minitab does these two calculations for you, so you'll have to do these by hand. But these are a lot simpler than the one we were just doing, because to find the mean, you simply multiply the number of trials you have times the probability of success. Pretty straightforward. For the standard deviation, it's the number of trials times the probability of success times the probability of failure, and then you take the square root. Again, those calculations are a whole lot easier than the ones we just had for general. Okay. So let's see, looks like by my phone, we've got 9 minutes. So let's see if we can maybe look at one example, and then if need be, we'll look at some others on Thursday. So this question says about 32% of students participate in a community volunteer program outside of school. If 20 students are selected at random, find the probability that. And then on the right-hand side, they give us several examples. Okay, it tells us that X is the number of students who participate in a community volunteer program outside of school, and P of X is the probability that they do that. Now, just to walk through those 4 conditions, because it doesn't tell us that it's a binomial, but I'm going to kind of think about it here. So the first condition is that I have a fixed number of trials. Well, it tells me 20 students are selected at random. So N, the number of trials that I have, is 20, because we're going to survey 20 students or select 20 students. Well, in terms of my outcomes, they're either going to participate or not participate. Those are the 2 outcomes. They either participate or they do not participate in the program. So I do have 2 outcomes. The question itself gives me the probability of a success, which in this case, a success is that they participate, and it tells me it's 32%, which I'm going to convert to a decimal. Let's see. The fact that student 1 participates, I don't think would influence whether student 2 does or student 3 does. So the trials are independent. And I can assume that the probability is constant because they're basing it off of a historical, you know, probably what's happened in the past. So I have to assume that it's going to be constant. So in this scenario does represent a binomial distribution. Okay, it didn't formally ask me that, but I've walked through those conditions to kind of verify that it is a binomial. The only other thing you might want here, okay, remember probability of participate is success, so that's P. The other piece that you may want or need is Q, which is the probability of failure, or in this case, that they don't participate. And that would be 1 minus P, or 1 minus 32%. So is that 68%? Okay, so the probability that they don't participate is 68%. Okay. I really think I want to stop at this point because I only have 5 minutes left and I don't know that we can get through everything in Minitab, and I don't want to totally leave you hanging. Okay, so we can look at those examples in the next class, which will be Thursday. So hopefully Thursday, the plan is we will finish binomial and begin a discussion of the continuous. We'll be looking at uniform and exponential. I hope we'll be able to get through that. If not, we'll adjust accordingly. But before we go, do you have any questions? And I'll try to put together that spreadsheet for the general and post it into the course this afternoon. Do you have questions before we go?